All right, so this is an ALEKS topic that's called identifying hybridization in a small molecule. And I think this is a really good topic because it also tests our ability to draw Lewis dot structures. So we have to draw the Lewis dot structures properly. If we don't draw the Lewis dot structures properly, then you're going to get it wrong. So the first thing that we're going to do for all of these, and in this video I'm going to go through 3 different examples just to sort of reiterate some points. But the first thing we're going to want to do is draw the actual Lewis dot structure. So for BO3 3-, the best Lewis dot structure looks like this, where each of my oxygen atoms has a formal negative charge. The boron is breaking the octet rule, but that's okay, because this is going to be the structure that minimizes formal charge, but also follows the octet rule for oxygen. Oxygen is always going to follow the octet rule. So this structure here is the best Lewis dot structure for BO3 3-. So again, if you didn't start with that, right, then you'd be out of luck. You would not be able to solve this problem. So the next thing I'm going to think about is the electron geometry. So around borons, the electron geometry is going to be based off of the number of electron groups around that boron. There's going to be 3 electron groups. And so then that's going to be a trigonal planar arrangement of those groups. So if I drew this sort of in the proper orientations, I would have boron, oxygen, oxygen, oxygen with 120-degree angles. So this is telling me that, trigonal planar, 120-degree angles, that I've got sp2 hybridization. So sp2 hybridization is going to be where I've got 3 different groups that are arranged 120 degrees apart from one another. That's going to be how we get to that, that configuration, that electron geometry. So the answer for this one is sp2. I'm just going to base my answer based off of my Lewis dot structure. All right, so let's do some more examples. And at the end, we'll do sort of a summary. So the next one says, what is the hybridization around phosphorus hexachloride, so PCl6? So right away, when I see that PCl6, to me, that indicates that I'm going to have a structure that looks like this with 6 chlorines around that central phosphorus. The phosphorus is going to have that formal negative charge, so I've got to have a formal negative charge here. So if we think about the phosphorus, 5 valence electrons minus 0 lone pairs minus 6 bonds equals -1. So we're going to have a negative formal charge on the phosphorus. So this is the best Lewis dot structure. Yes, we're breaking the octet rule for that phosphorus, but we're following it for all the chlorines. And we've got formal charges of 0 for all the chlorines. So this is the best Lewis dot structure. And I've got 6 groups, 6 electron groups. So the way that I'm going to get, a proper hybridization for this is going to be sp3d2. And one way to sort of think about it is you're going to need to fit all of these electron groups into the different hybrid orbitals. So if I've got 6 electron groups, I'm going to need 6 hybrid orbitals. So 1 plus 3 is 4, plus 2 is 6. So if you add these up, you get 6 hybrid orbitals, right? sp3d2, I've got 6 different spaces for my electron groups. So that's going to be my answer for this one, sp3d2. All right, let's do one more, and then we'll do a summary. So this last one is SF3 minus with a -1 charge. So the sulfur is going to be in the middle. Then I'm going to have my different fluorine atoms. And then this sulfur is actually going to have 2 sets of lone pairs. So if you count up the number of electrons, we should have 28 electrons in our structure. So if you add up your valence electrons, we've got 28. If you count all these, we end up with 28 electrons. The sulfur is going to have that formal -1 charge. Again, we're breaking the octet rule, but we're minimizing formal charges as much as possible for this structure. So this is the best Lewis dot structure. And I've got 1, 2, 3, 4, 5 different electron groups. 5 electron groups. Therefore, it's going to be sp3d as the hybridization. Again, I'm going to fill in however many electron groups I need. So sp3d is my answer there. So let's go through just sort of summary. So if you've got electron groups. If you have 2, 3, 4, 5, 6 electron groups, so this would be the number of electrons around your central atom. And then the hybridization. If it's 2, it's going to be sp. If it's 3, it's going to be sp2. If it's 4, it's going to be sp3, 5, sp3d, and 6, sp3d2. Getting a little messy there. And then let's talk about the angles. Let's talk about the angles for these three. This is probably the most relevant. If we've got 180-degree angles in our molecule, if it's a linear molecule, we're going to have sp hybridization. For sp2, it's going to be 120-degree angles, and for sp3, it's going to be 109.5-degree angles. And those are really the most important, right? So as we move forward, these are going to be the ones that we want to make sure we understand and focus on. So if your molecule is linear, then you're going to have 180-degree angles, you're going to have sp hybridization. You have 2 electron groups around that central atom. This is going to be trigonal planar, and this is going to be tetrahedral. So these names refer to the names of the electron geometries, and then we could have different molecular geometries based on the number of lone pairs that we have, but that's another video for another day. All right, hope that helps.